Now that we've completed our introduction to special relativity, what we want to do now is go beyond. And it's immediately evident what we said before is that we ignored gravity in all our cases, even though we had Gedanken experiments that may have taken place in Earth-like scenarios. It was implicit that there was no gravity in any of the scenarios we considered before. Now we want to change that, and we want to start thinking about gravity, but as I just said, it has to change. And Einstein knew this. He knew this in 1905 immediately, and he took another 10 years to come up with a theory that would incorporate gravity in a relativistic scenario. So why does it need to change? And why is it obvious that it needs to change? Well, you go back to Newton's universal law of gravity. Recall we have this. This is the law of the land, if you will, for gravity up until 1905. And it was, experimentally well founded. We won't go through the history. There were some differences observed that could not be explained. The progression of the precession of the perihelion of Mercury, for example, but we won't get into that. But there is just just looking at this expression here, there's a direct reason why this cannot work. And the reason is if you look at this, the question is, how fast is the influence of gravity mediated? Well, there's nothing in this expression that tells how fast it's mediated, and thus it must be instantaneous. And it was known to Newton and others as well, so it's not like it's any new discovery. But what we found in special relativity is that if we have instantaneous interactions, that can violate causality and lead to a logical contradiction. So that's just a kind of a basic point of why we need to change things. Now, we want to say gravity needs to change, but again, what we're doing is we're just generalizing the special theory of relativity. So that's why it's called the special and the general theory. Okay, so Einstein undertook this, and it wasn't until 1907 that he came up with something he said was the happiest thought of his life. And it goes to a question that I often ask little kids, whatever, or actually students, is, do you feel gravity? And if you ask this question of most people, they would say, yes, of course I feel gravity. I always complain every morning when I get up that who turned up the gravity, for example. But is that really what you are experiencing? And if you give it any serious thought, you can quickly convince yourself the answer is no, that you do not feel gravity at all. And again, you may not buy this at this point, but we want to kind of go through this related to the discussion of what Einstein came up with in 1907, which is known as the equivalence principle. So to do this, we want to kind of come up with a Gedanken experiment. And so we're going to take Bob, and we'll have Alice too hanging around, but Alice will usually be like Earth-based, perhaps. But we want to consider Bob in a small, isolated elevator car. It could be a little rocket ship, whatever. Just a small box that he can't really look out of. And we want to consider his frame of reference within that box. And we want to consider 4 different scenarios. So the first is we want to think of just free-floating in deep space. So here's this example here, and he does a physics experiment. And so let's just say, like it's as shown, he holds a ball and he lets go. We can imagine what's going to happen. Now, this is the story we're talking about in special relativity, so it's clear that this is an inertial reference frame. There's no external forces on him. He's just free floating in deep space. Okay. The next case is we'll just put Bob on the surface of the Earth. And again, this is a pretty obvious one. But again, we want to look at these different cases. So again, here's Alice and Bob. And again, he'll drop the ball again, just like he did in the previous case. But in this case, we know what happens. You just pick up anything around you, drop it. It accelerates down at 9.8 meters per second squared. Okay, that's the next scenario. And again, those are the ones we want to kind of examine. But again, we'll take those as our kind of givens. But we do want to go further with this. Next, we want to take the elevator car and we want to drop it from rest. A sizable height up, such that we can actually carry out this physics experiment. And so this will look like as follows. Let's just make it big for a moment. And so again, Alice will say it sits on the surface and watches this happen. And again, Bob does the same thing. He holds the ball out in his hand and he lets go. What does he experience? Let's watch that again. Well, now this may be unfamiliar to you. It may or may not be, but it is true that if you, even in Newtonian physics, in this case, everything accelerates down at the same rate. So there are no internal accelerations within the box. So everything floats, essentially. There's no relative acceleration. He lets go of the ball. The ball's not going to accelerate down from the point of view of Bob. Be careful there. It's just going to sit there and hang there as it falls. So he will experience free fall. And that's exactly what that is. This is equivalent to what the astronauts in the International Space Station are experiencing. Okay, so that's that example. And again, we want to come back to what the experiences of Bob are in his small little ship. Lastly, we want to put a rocket on the elevator car. And again, it could be a spaceship. And we want to take it to deep space, and we want to accelerate it upwards at 9.8 meters per second squared. So what happens in this case? Well, again, if you give it a little thought, that Bob will experience essentially what he experiences on Earth here. He lets go of the ball. The ball's going to accelerate from his perspective down to the bottom of the floor. It's accelerate down to 9.8 meters per second squared. Of course, from Alice's perspective, when Bob lets go of that ball, it's momentarily, while it's falling, it's actually traveling at a constant velocity from Alice's perspective, who's free floating out in space. We got to make that clear. Alice is free floating, and so this is what occurs. Now, you probably have heard this before, but at least this is the setup. Is that when Bob carries out this experiment in each frame, we get the following pictures. Well, first of all, when we looked at scenarios 1 and 3, so let's bring up an animation of that. 1 and 3. Here's 1 and 3. Oh, that's not 1 and 3. There it is. Look what happens in both cases. They're identical. The physics, at least for the simple experiment, is identical. Bob cannot tell whether he's free falling in a uniform gravitational field or he's in deep outer space. He has no windows, he can't tell. That's the first thing we learn. The next one is, if we look at the other two scenarios, let's bring those up. That's scenarios 2 and 4. 2 and 4. Here they are. And again, we examine what happens in both frames. Go. There we go. We see that within Bob's view, Bob's frame, the same thing happens. So what this says is that scenarios 1 and 3 are equivalent, and scenarios 2 and 4, which are these two, are equivalent. Now, the thing to note here is that may seem obvious, perhaps not, but you do want to check that. But note carefully, it changes things significantly. Because, and this is what Einstein brought up to a principle, saying that, well, if scenario 1 is clearly an inertial reference frame, that's where you're floating in deep space, we're obvious, we can't doubt that pretty much, and 1 and 3 are equivalent, that says that scenario 3 is also an inertial reference frame, because the laws of physics, from Bob's perspective, are going to be identical or equivalent in those two scenarios. Or, we can also say that clearly scenario 4, where the elevator car was accelerating at deep space, that's clearly not an inertial reference frame. That tells us that scenario 2, being equivalent, is not an inertial reference frame. This is the change, because this is, if you learned in your grade school physics, when we sit here on the Earth, we're approximately an inertial reference frame, and if you're free falling, you're accelerating, then you're not an inertial reference frame. But here we're seeing that that's not really the best way to think about it, because we want to think about the fundamental physics that's going on. If the physics is the same in 1 and 3, And one of those frames is an inertial reference frame. The other one has to be an inertial reference frame based on physics. This is why if you ever we're told that an inertial reference frame is one that's not accelerating, that's not the definition. It's one where Newton's laws hold true. Okay. But again, this is the essence of what we call the equivalence principle. And let's just state it. So, and put some caveats and filled in a little bit. But physics in a free-falling frame, where it's in a uniform gravitational field, is equivalent to the physics in an inertial reference frame without gravity. Now, let's be careful here. And when we talk about this, Bob in the little box, that needs to be small enough so he cannot tell that there's any change in gravity within his box. Because clearly, if we had the Earth here, and Bob had a really wide box, and Bob's in the middle, and two balls were released on either end at some point in time, and it's free falling, everything's free falling, well, clearly these, the accelerations would be like this, and clearly these balls would actually accelerate towards Bob, and he would see that. So that means that, we need this frame to be small enough such that you cannot detect any variation in the gravitational field for this equivalence to work. Now, technically what that means is that we have to consider this principle to work at each point, or event. And so really when we say locally defined frames, really it should be a point. But we'll consider, a box like Bob we had over here. Okay, another way to say this, as we said, the second one, is that the physics in the frame with a uniform gravity, which again, the frame's fixed to the source, so on the surface of a planet, say, is equivalent to the physics in an accelerating frame of reference. And again, where it's accelerating in the opposite direction, but at the same magnitude of the acceleration due to gravity in whichever source that is. And the second one you can use to learn some new effects. And we will come back in a moment to employ the equivalence principle to learn about some new effects that come around in general relativity when we're in gravitational fields. And again, we could talk about a number of them, but we're just going to hold off to the first one just to keep it simple at first. But we want to kind of return to our geometrical view, because what this is telling us is that the geometry, as always, is the key, and we're finding out that something's awry, is going wrong. So let's think about this carefully, and we're going to find a new metric is needed. And let's show how that works. So I want to take two objects here, and again, remember the principle of maximal aging. Recall that it said that the inertial reference frame is the one that experiences the maximal proper time between two events along its world line to occur. And in special relativity, that was the straight world line, of course. Now consider dropping two clocks from, say, 1 kilometer above the surface of the Earth. We do this, again, so we have some distance here to deal with, and we'll assume the gravitational field is constant as well. So, but we want to consider these two objects that take different paths between two events. They're dropped at the same time from the same point location. One just free falls to the ground, and again, we'll ignore air resistance. B travels with a constant velocity. You might need a parachute or an engine to do that. But what we want, we want them to, event one, we'll call it, they're released at the same time, and we want them to arrive at the ground at the same time. We can arrange that, we just have to adjust the speed of object B to do that. So let's take a look at that in terms of a space-time diagram. So here's a space-time diagram now, where object B is the straight world line between, and again, we'll take this to be, this is the ground level here, this would be 1 kilometer where event 1 is. And then they hit at event 2. Clearly the red one is curved because it's accelerating in this frame of reference, and that's object A. Now, we want to think about this in terms of our metric, but remember what we said before is when we talked about our flat metric, which I'll put up here again just to now again we'll just consider one dimension here just for simplicity. That the straight world line was the one that had the maximal proper time, which is B. So B has the maximal proper time going by. Push that off the side. Okay, because again, in the flat space-time with our metric, the straight world line has that maximal proper time. Now, what the principal maximal aging said is that the inertial frame is the one that has the greater proper time to pass. But the equivalence principle we just said is that in this particular case, object A should be the inertial reference frame because it is free falling in a uniform gravitational field. It's equivalent, the physics within that frame, is equivalent to one in deep space away from any gravitational sources and is at rest or moving some uniform velocity. And so the equivalence principle says that, well, this one should have the greatest proper time. And if you integrate the metric, I mean, it's pretty obvious, you're going to get different answers. And because of what we've done before, B is going to give you the greater proper time passing. Now, so what does that tell us? It tells us that this flat metric we've been discussing, again, let me put it up here again, is not the right one for the scenario because it doesn't give us what we now demand. So the flat metric that we've been talking about up until this point is not the appropriate one when we're in a significant gravitational field. And we'll expand on this, what we mean by that. But right now we can consider in this frame that's fixed to the surface of the Earth. It's not the appropriate one. Now let me go ahead and jump ahead a little bit here. Notice that if we transform to the frame of object A, which is free falling, and say it's in a little box like Bob was, well, within that box, as long as it's small enough and that you don't notice that there's no variation in gravity, if you will, that can be described by a flat metric because that's equivalent to the inertial reference frame. So here we see that the free falling observer in that small frame has a flat metric around them. Sometimes this is said that you can transform gravity away by going to an accelerating quote-unquote reference frame, free falling. But what we're finding here is that the free falling observer is actually the more natural movement through space-time. Again, there's no electromagnetic forces acting on these objects. And A, I should say. B obviously does, because it needs an engine to do this. So we see that the greatest proper time passage must be A, and that's what we're going to call a geodesic, which is the equivalent is, again, we'll expand on this later, is essentially on, say, the surface of the Earth. If you take 2 points on the Earth and you connect them by the shortest line, that's what we call a geodesic. It's a unique line that gives the minimal distance. In space-time, we have the geodesic being the unique line between two events that has the maximal proper time going by. And again, what we're seeing is that those geodesics are going to be curved. This tells us that space-time is curved. And we need to deal with curved spaces. So this is where we come back to geometry. The next lecture we'll have to go and discuss a little bit more about curvature of spaces just to get us warmed up to talk about curved space-time. So let's, and again, so this connection here, what we're saying is that a gravitational field is equivalent to acceleration. Sometimes you'll see it stated as gravity is equal to acceleration. And that is equal to now curved space-time. Now I just want to kind of quickly here do another example to show the connection between acceleration and curved space-time, really curved space, but let's go on. But this demonstration here is telling us we have to change the metric, and that will come later. Okay, so I want to consider one of my favorite examples. We're just going to do a very simple analysis, and we're not going to go into this in any depth, but we just want to kind of get the point across. Consider what I call a relativistic merry-go-round. And we want to consider going around at 87% speed of light, so gamma is equal to 2. We have a dilation factor of half. We will have observers, A, all along the outside, represented by these black dots. These are observers that are fixed to the ground, say. Again, we'd do this in deep space. We don't care about, we're not talking about considering gravity here. And this this merry-go-round rotates obviously very fast, and there are issues with how it got to this state. There are theorems that you can't do this with any solid object, but we'll just assume that somehow it was set up that this arrangement exists. And we'll have one observer on the edge. We could have more, but we'll just take one. We'll call him B. And that could be the child. These could be the parents watching, and that could be a child, whatever. Now, what we want to do is look at how they look at this merry-go-round, the geometry of it, really, and the shape and the size. So the A observers, now again, this can be done in different ways, but if they just note the distance between them, which I'll call delta A here, is just going to be the distance to each, and they're equally spaced. All they need to do is count them. If there's n of them, then the circumference of the wheel is just n times delta A, clearly. And the radius here, they can measure, say, separately, and they'll find, yes, of course, it's going to equal to 2 pi r, right? But let's look at from observer B perspective. And a way that observer B could measure it is to count the observers as well. And again, we'll put numbers on them so they know, so the observer B knows when they come back to the same observer, say, and count them and use that distance between them as well. Now here, the important thing to note is that for observer B, the radius is the same because it's perpendicular to the tangential velocity. So there is no Lorentz contraction for the radius, so they measure the same radius. And it's supposed to be delta A prime, but they measure a distance between the observers here of delta A prime, let's say. Well, clearly, because we know that observer is going to see those observers closer together, then we see that what we only care about here is that the circumference as measured by the observer B is not going to be the same as it is for those on the edge. So what that means is that this result here, that the circumference of a circle is 2 pi r, is a Euclidean geometric result. It does not hold in frame B. And that's telling us that the space is curved. And so this is just a kind of a quick way, another way to think about acceleration relating is equal to curved spacetime if we take these relativistic effects into account. So we have now the kind of the setup and the motivation to get the changing geometry of spacetime to give us gravity. But we're going to hold off on that until we get the full statement. But again, the idea is now objects will travel through spacetime in the most natural way unless acted upon by an external electromagnetic force. And we're not considering gravity. Gravity is essentially now a pseudo force, if you will. That it's not a force at all, but it's just the natural movement of objects through spacetime, a curved spacetime, that seems to us normally, like for Newtonian intuition, look like gravity. But it's actually just... and again, the way to think about it is if you're sitting in your chair right now listening to this, your natural motion through spacetime would be to accelerate down to the center of the Earth. However, there is an electromagnetic force, a net force on you, holding you up in place, so you don't do that. So you stay at rest. So that external net force, that electromagnetic force, it changes the scenario, so it's not an inertial reference frame anymore, because there's a net force on the frame. Okay, now let's. I want to return to the equivalence principle and talk about one effect just really quickly to show how this works and how you use the equivalence principle to see some general relativistic effects. So let's take a look here now, and let's go back to Bob now. And this is kind of a standard way to argue with the equivalence principle. What we want to do is consider Bob in a elevator car again, of course, and we want him to have the rocket, so it's accelerating, and he's going to accelerate at g. And he's going to have a laser on one edge of his box, and it's going to fire across the box. And so we want to watch this as this happens. It's not going. Oh wait, here we go. So notice what, now this is greatly exaggerated. I just want to point this out. This is much effect. I'll talk about the magnitude in a minute. However, just note that because the velocity of Bob is getting larger as it goes up, and the laser was fired with some component, straight across and straight up, as shown there, that because of the constancy of the speed of light, the elevator car would have moved a little bit further than the light would have gone, and so the light's going to hit a little bit lower on the opposite wall. And so from Bob's frame, what he sees that, oh, it drops a little bit. So we take this as evident, because this is just kind of simple physics reasoning of how this looks. So from Bob's perspective, again, always Bob's perspective, the laser beam appears to fall, if you will. Here's where we invoke the equivalence principle. We say, well, remember this frame here, which was the frame 4 in our scenario, is identical to frame 2. So we go back and we look at the frame here, where now Bob's at rest on the surface of the Earth. Well, what does he see? He sees that the light bends down. So this is just a quick way to see that, well, light's going to be affected by the curved spacetime. Actually, everything is, but light is also. Whereas in Newtonian physics, again, the basic view is that light is not affected by gravity because it has no mass. Here we're seeing that, oh, light is affected if we were thinking it as gravity, but it's not gravity anymore. It's a curved spacetime. Now, just to give you an idea of this effect, again, it's greatly exaggerated. So just to give an idea, what would be the magnitude of this effect on the surface of the Earth? Well, just imagine that I take this laser and I fire it horizontally, and assume we're not going to consider the curvature of the Earth, even though we probably should, but we won't. Let's say somehow we have a 1 kilometer uniform gravitational field, and we fire this exactly perpendicular to that gravitational field. How far would it fall after 1 kilometer? Well, it turns out it's about half an angstrom. So about the size, roughly about the size of a hydrogen atom or so. So it's a very weak effect, what we're talking about here. That's why it's greatly exaggerated. But has been measured. Not that direct experiment, of course, in other ways, I should say. So there are other effects we can talk about, and there's going to be a number of what we call general relativistic effects. Time is going to change, redshifts, and various other things, which we'll come back to in a later lecture.